In this video, I'm going to take a look at some terminology and breaking down these three-dimensional solids, which we call polyhedra. If you take a look down here at this shape, this polyhedra here, first I would challenge you to, what is the name of this polyhedra? So if you pause a minute and look at it, hopefully you notice you have a base here, and then rectangles on the sides, and then another base on the bottom here. So that tells you it's a prism because it has two bases, and it's a five-sided figure, so it's a pentagon. So it's a pentagonal prism. Pentagonal prism. Now, if you look at class activity 13A, it will outline this a little bit more, but it basically challenges you to make some polyhedra using toothpicks and gumdrops or little clay balls. So maybe if you have a younger sibling or somebody, you could do that with them if you wanted to. But then it asks you to visualize and predict for a rectangular prism. How many toothpicks would it take? So pause a minute and think about if you had a rectangular prism, how many toothpicks would you need, and how many clay balls would you need? So I don't know how you thought about it. I'm picturing 4 toothpicks on the bottom for the base, 4 toothpicks on the top, so 4 on the bottom, 4 on the top, and then 4 up and down. And that's not a very good picture, but that would be 4 times 4, 4, and 4. That's a total of 12. How many clay balls would it take? Well, I'm picturing 4 on the base and 4 on the top, so that would be a total of 8. Now, if you read in the class activity 13A, it says you can actually take some soapy solution, soapy water, and dip these polyhedra in there, and it'll actually kind of make a soapy face. And so that's actually another category I'm going to add. How many faces would be on this rectangular prism? I'm seeing 1 on top, 1 on bottom, and then 4 around the edges. So that would be a total of 6. 2 and 4 is 6. Now, a triangular prism. How many toothpicks, how many clay balls, how many faces? Go ahead and pause it and think about it for yourself. I'm picturing 3 on the bottom, 3 on the top, and then 3 up and down. So 3, 3, and 3 is 9. How many clay balls? I'm picturing 1, 2, 3 on top, 1, 2, 3 on the bottom. That's a total of 6. How many faces then? I have 3 rectangles here on this lateral sides, and then the triangular top and bottom, so that's a total of 5 faces. Maybe before I do the next 2, I'm going to skip to the next slide. Just some vocab. The face is a polygon that makes up the outer surfaces of the polyhedron. The edge, on the other hand, is a place where 2 faces come together. If you think about it, what is that in our picture here? Where is it where 2 faces come together? You could see this face, this rectangular face, this pentagonal face come together at the toothpick. So we can think of this edge as the toothpick. And then the vertex is the point where several faces come together. We can think about that as the gumdrop or the clay ball. All right. So using that terminology, toothpicks are edges. Clay balls are vertices or a vertex. So how about a pyramid with a triangular base? Okay, pause it again and think through that. I'm picturing a triangle at the bottom. There's 3 there. And then a point up here that's going to 1, 2, 3. So 3 and 3, it's a total of 6. Clay balls, I've got 3 on the bottom, 1 on top. That's 4. And then faces, I've got a triangle on the bottom, and then 3 triangles on the sides. That's a little harder to see, but a triangle on the bottom and 3 on the sides. How about a pyramid with a square base? Go ahead and pause it and think through that on your own. Alright, so I'm thinking of the base as a square, so that's 4 toothpicks. And then a point up top. I'm going to need 1, 2, 3, 4 toothpicks to go down to the base. So 4 and 4, that gives me 8. How many vertices does it have? 1, 2, 3, 4, and then 1 at the top. That's 5. And how many faces? I've got 4 triangles on the sides, and then 1 square base. So that's a total of 5 faces. Okay. Now, for this course, that's going to be sufficient. We're going to just look at terminology and understanding them. There is something interesting that I want to point out here, and that's called Euler's formula. Again, this isn't something to memorize or even that I'm going to test you on, just kind of an FYI. Euler was a mathematician. He gets credit for this formula, that if you take the number of vertices plus the faces, it's equal to the edges plus 2. So let's go back and take a look at this. So his formula was vertices and faces added together equals edges plus 2. Check it out. 8, 16 is 14. That's 2 more than that. 6 and 5 is 11. That's 2 more than 9. 4 and 4 is 8, which is 2 more than 6. 5 and 5 is 10, which is 2 more than 8. And so Euler's formula works for any polyhedra that we can create. Quick review. Looking at polyhedra, the edges are called, where the faces come together are called edges. Where multiple faces meet is called a vertice, and the actual face is the flat part